Welcome back, everybody. Well, past few days, we've been thinking about line integrals. We started off with our kind of standard line integrals, and we've then thought about projected line integrals, and we even thought about what it looks like to compute a line integral in the presence of a vector field. Today, we're going to ask a question that will continue asking throughout the rest of the semester, and that is, how does our fundamental theorem part 2 generalize to higher dimensions? And we'll actually see a number of different ways that it generalizes in different contexts. And the first way that we'll see actually shows us that we get a beautiful generalization when we're computing line integrals of gradient fields. And so to start in, let's think about what FTC2 says. So the basic setup, right, is we have some interval from A to B, and we have some derivative information at each point. And fundamental theorem says, well, we can either add up all of our information from A to B, right, adding up our derivative information, or we can just take an antiderivative, right, f, and evaluate at B and subtract what we get when we evaluate at A. And what I claim is that this expression on the right has a nice kind of way of thinking about it. This is the net change in our function f, right, over our interval from A to B, right? This is our function value at the end minus our function value at the start, right? This will show us the net change in our function from the start to the end. Now, what the fundamental theorem of line integrals says is, well, let's say we don't maybe just have an interval. Maybe we have, instead of our interval, maybe we have a curve, say in 3 space. And maybe instead of, just some f prime derivative, maybe we have a gradient field. Right? Gradients use our partial derivative information. And so we could think about computing the line integral of our gradient field. All right? And so this left-hand side reminds us, or rhymes with, looks like this left-hand side up here. Right, where instead of an interval, we're integrating over a curve. Instead of our just derivative, we have our gradient field. And what's nice is that what the fundamental theorem for line integrals says is that, well, what this integral equals is exactly what it did before, the net change in our function f from the start to the finish. And so here, this arrow right here is showing us the direction that we're moving along our curve. And so to write down the right-hand side in full, we just need to give a little name to each of these points. So the starting point, let's say, has coordinates x1, y1, z1, and the end, let's say, x2, y2, z2. And the net change in f is just f of that endpoint, x2, y2, z2, oops, that's just a parenthesis, minus f of the start point, x1, y1, z1. And so we get this very nice generalization of our FTC2 when we're doing a line integral for a gradient field. The proof of this result is not too crazy. It's a quick application of actually our standard, parameterize and translate process for computing line integrals, and the multivariable chain rule shows up. It's in the text, and I encourage you to look at it there. But we won't go through the details here. What I will say is that the full result, the fundamental theorem for line integrals, does assume some niceness on the situation. For example, that our curve is smooth and some niceness on our function f. We won't need to worry about the details. What I want to highlight is that this result, the fundamental theorem for line integrals, in a similar way to how our FTC2 allows us to bypass the kind of standard method of computing a Riemann sum and the limit to compute this integral, we get to bypass that and just find the net change in our function. The fundamental theorem for line integrals allows us to bypass our standard two-step process, right, where we first parameterize our curve with some vector function and then translate the line integral using our catchphrase and work it out. This allows us to completely bypass that and just find the net change in our function. Well, it's very nice when we can use it. And so right away, let's look at an example here. And so here, we're computing a line integral for a gradient field where our function f is here, and our curve c is parameterized to this vector function for t from 0 to 1. Why don't you actually right now pause the video and see if you can make use of the fundamental theorem for line integrals just above here off the screen and the information given here, and see if you can use the fundamental theorem to compute this line integral. All right, well, let's talk through how this goes. Right, the fundamental theorem for line integrals tells us that our line integral for our gradient field equals just the net change in our function f, right, from our start to our finish. And so what this allows us to do is, well, if we want to compute this line integral, well, we just need to figure out this net change. And this is a much cleaner and quicker side of the equation to figure out. All we need to figure out is, where is our starting point and where is our ending point. And so here, right, here's our parameterization, which defines our curve. And whatever our curve looks like, it's doing something that has some starting point at t equals 0, has some stopping point at t equals 1. But if we look at our function, we can't plug in these t values to our function f, right? F is a function of x and y. We need to figure out x, y coordinates. And so, well, the way we do that through our parameterization takes in t values and spits us out x, y. And so we just need to take these starting t and ending t's and plug them into our parameterization. And if we do that here, it's being careful with our trig, our parameterization at 0 is giving us the point 1 minus 1, and our parameterization at the point 1 is giving us the point 2, 2. And so here's our starting point, here's our ending point, and so we have f of our end minus f of our start. And at this point, we can just take these and plug them into our function and see what we get. All right, working this out, we end up with 15 as our final result. And a couple things I want to point out about this example. The first is that this side of the equation here, the net change in f, this is so much cleaner and quicker to work out than our 1-2 step process of parameterizing a curve and translating the line integral and integrating. And so when we can use the fundamental theorem for line integrals to compute a line integral, that's definitely the way we should go. It's going to be much cleaner. The second thing I want to highlight is that the fundamental theorem for line integrals only tells us how to compute line integrals for gradient fields. Right? And that's like super duper alley-ooper important to notice, because not every vector field is a gradient field, right? So if we're just doing a standard line integral for some vector field, right? At least in this form, where we're not sure if we can use our fundamental theorem for line integrals, right? Only if we're definitely computing the line integral for a gradient field can we use our fundamental theorem here. All right, so we can't always use fundamental theorem. We can only use it if the vector field we're integrating is actually a gradient field. Okay, so I have a question for you. So, using our original curve, right, starting at 1 minus 1 and ending at 2, 2, our computation just a moment ago shows that the line integral for our gradient field along that curve has the value 15. My question for you is, well, what if we changed the curve? Kept the same gradient field, but what if we changed the curve to the straight line segment from 1 minus 1 to 2, 2? What would be the value of the line integral along that curve? If you said 15, you are spot on. Right? The reason why, right, is because, well, here we're doing the line integral of a gradient field, and right, the fundamental theorem for line integrals tells us, well, this is just going to be f of our end minus f of our start, right? But we have the exact same starting and ending point as we did before, and so just like we did above, we're going to end up with 15. And so notice, right, if we chose some other curve, right, if we started here at 1 minus 1 and went wee like this and just kind of, followed our heart and then ended up at 2, 2, right? And let's call that, I don't know, C tilde. Well then, the line integral over C tilde of our same gradient field, dr, is going to have that same value. 15, right? Because it has the same starting point and ending point. And so we see here that it actually, we're going to get the exact same value no matter what path we take from 1, minus 1 to 2, 2. So we'll get the same value no matter what path we take from the start, 1, minus 1, to the finish, 2, 2. And because of that, because the value for our line integral we get is independent of the path we choose, we say that gradient fields are independent of path. Next question for you. What if we did the line integral instead of just over our first curve, but we actually did a loop where we first did our curve and then came back along C prime. So that would look like up here, going along our curve C, and then coming back along C prime in the backwards direction. Right, if we did a loop like that and computed the line integral, what should we get there? Well, here, if you said 0, you are spot on, right? The reason being is because, well, when we go across C, right, we'll get 15, and then when we go backwards across C prime, right, we're going to get the negative of what we had before, and so we'll get plus negative 15, which will give us the 0. Or another fancy way to think about this, since we started at 1 minus 1 for this loop and ended at 1 minus 1, right, the 0 we could also think about as f of 1 minus 1 minus f of 1 minus 1. Right, we have the same start and stop point, and so the net change is going to be 0. And so here we actually kind of are seeing this general property that if we have a gradient field, which are independent of path, then if we integrate along a loop, we're going to get 0. And in fact, what's true is that completely characterizes this idea of being independent of path. So a vector field is independent of path for its line integrals if and only if the value of those integrals along any loop equals 0. And a loop, a fancier name, a more mathy name for a loop is just a closed path. Right, it just means the same start and end. Right, and so line integrals for a vector field are independent of path if and only if the line integrals are 0 for any loop in our vector field's domain. All right, so this is another way that one can think about this idea of being independent of path. So this property, being independent of path, that gradient fields have is really useful. It's nice to be able to know that you're going to be able to use any path you want, and it won't matter. The result you get will be the same. So a natural question is, well, hey, are there any other vector fields, besides gradient fields that have this property? And the answer is no. The result here says that so if line integrals for a vector field are independent of path, then that vector field is a gradient field. Right, in other words, there is some scalar function, little f, whose gradient field is our vector field. And so this is telling us that the only vector fields that are independent of path are gradient fields. And the proof of this is not one that we'll go through in detail, but I do want to say just a few words about it, because this is a really nice situation that comes up in mathematics. So to start, the theorem above, first of all, needs to make sort of some assumption on the context. And so the first assumption it makes is that our vector field, capital F, is defined on an open connected region. And so the idea here, open, right, the kind of idea here, if we say an open interval, we mean an interval where we don't include, the boundary points. Well, similarly here, an open region is a region where we don't include that boundary edge. Next, connected region, it means exactly what it sounds like, just we have one piece, not a bunch of separate pieces. Okay, and so, right, the setup here is that we have some vector field, capital F, and that vector field is giving us, attached to each point in our region, a vector, right? So attached to this point, we have a vector, attached to this point, we have a vector, attached to this point, we have a vector, right? Attached to each and every point, we have a green vector coming from our vector field, capital F. And so what we're claiming is that, if this vector field is independent of path, then it's actually a gradient field, right? There's some little function f whose gradient is our vector field. And just at the start, it's not immediately clear at all how to find that function. How could we possibly come up with that little function f? And this is actually a really cool example of a situation where it's really the only function that we can write down that meaningfully uses all of our information. And so I just want to talk through that a little bit. So, okay, so we want to come up with some scalar function, little f, right? And so this little f is going to take in any xy here that we'd like to give it and spit us out something, right? And so say if we give it this xy, right, we want to get something outputted from our function. And well, what do we have on hand? Well, we have a vector field, and right, we know something about line integrals. Right? Well, so let's think about that. Line integrals give us numbers, and so maybe what we'd like to do is, once and for all, let's pick kind of a base point down here, some point AB, and let's say, well, that what our function f is going to spit out is from taking a path from our base point here up to our chosen point xy that we're thinking about. All right, so let's move along this curve and let's spit out whatever we get from our line integral. So the value of our line integral of f dot dr, right, where we move along this curve here. And so at this point, this is pretty nice, right? We're using line integrals. This meaningfully is using, say, the point that we plug in, and we can get some number from this. So here's a thought, though. We made a choice, right? But from moving from AB to XY, we went along this path. What if you wanted to use a different path? Maybe you, being you, wanted to go along this path over here, and you said, this is the path for me, this C prime. This is what I want to use. And the question is, is that okay, right? And what if along this red path we got 15 like we did before, but along this blue path you got 7, right? We can't have both 15 and 7 being the output of our function at xy, right? We need a unique output. But here's the beauty of our setup. What do we know about our line integrals for our vector field? They're independent of path, right? So no matter what curve that we want to take from our base point AB up to our point we're plugging in, xy, we'll get the same thing. And so here, our value doesn't depend on the path that we use. And because of that, this function is well defined. And it turns out that this is the function that one can use and show that its gradient field is exactly our vector field f that we started with. And the proof is in the text. I'd encourage you to check it out. It's a cool argument, but this is really what I wanted to show us and talk us through this cool situation where the only thing that we can really meaningfully write down is exactly what works. All right, that's it for today. Good work, everybody. If you have any questions, post those to Piazza, and I'll see you next time.